In this video, we are going to introduce the exciting new features that are added to the Reliability Assessment module in ETAP 24. During the video, first we will learn how to model a system for reliability assessment study and what type of input data we will need to run the study in ETAP. Then we will review the different options that our study has, including some of the existing options and the new ones that are added in ETAP 24. And finally, we will look at the results that software provides for us after running the reliability assessment. For this presentation, we are using the one-line diagram of the distribution test system known as Roy-Billington test system, or RBTS. We are looking at the bus 4 of this test case system, which has a utility connected to the 33 kV bus bar. We have added the DG here as the backup generator connected to the 11 kV bus bar. There are also some switches here already in the system that will be used in case of certain failures to restore the power to some of these load points. So let's quickly review how we can model the reliability incidents in ETAP. Let's assume that we want to model the failure that may happen on this utility. So first we open the utility element editor and go to its reliability page. I need to enter the failure rate of the element, which is the probability that the element may fail over a life cycle of 1 year, here in this edit box. The data may be available based on the historical data, or I can use the ETAP library quick pick to get the value for each element from the IEEE Gold Books or IEEE Standard 3006.8. Once we have defined the element failure, we have 3 options for the timing. The first one is that we don't have any replacement or alternative supply passes embedded in the system. Therefore, we need to interrupt the supply and wait for the element to be repaired. This time interval for repairing the element is generally known as mean time to repair and is shown by MTTR. So I need to enter the value of MTTR in the system in forms of hours. As the second option, we might have a spare element for defaulted elements, so we can check this replacement available checkbox here, and then enter the amount of time that takes for the element to be replaced in forms of hour in this edit box. As the third option, we might have designed an alternative supply pass in the system such that once an element is failed, then it can be isolated from the rest of the system and the affected load points are supplied or restored through an alternative pass. The amount of time that it takes for this process is generally known as switching time, and we need to enter that value here in forms of either hours or seconds in this edit box here. As an example, let's say a failure happens on this cable 1. So once the cable is failed, first it is separated from the rest of the system through these 2 circuit breakers. Then engine will look at the design to see if it can find an alternative path for the system to restore the affected load points here. So in this case, we will have this alternative path here to supply the load through this tie PD here to the affected load points. So in this case, for this cable 1, I need to enter the amount of time that it takes for the switching action to be completed here in the switching time edit box. So in this case, for this example, it is 600 seconds or 10 minutes. Once we have defined the switching time, the failure rates, the replacement time, and the MTTR for all of the elements in the project file, then we are good to run the reliability assessment study. For that, I go to the power quality and reliability group in the ETAP 24, which is using the ribbon bar version. And then I run the reliability assessment from here. Once the calculation is completed, ETAP reports different types of reliability indices on the OLV. In general, it includes the failure rates, the interruption duration, either in forms of average or annual, at the load points, at the buses, or at the sources. If you're looking to get the value at the equipment level, then all you need to do is to add a bus connected to that element and then read the values for that bus, which resembles the value at the equipment level. Also, we report the ENS, or electrical energy not served, at the location of the load points. We also report the cost associated with the reliability incident or expected interruption cost as E-cost based on the load sector that is defined in the reliability page of the load elements. For the cost, you can always go to the sector type library and define different types of load sectors and define the costs here. Then the E-cost will be calculated based on that. In addition to the results that are displayed on the OLV, we can have a system-wide result. So I go to the report manager here and create a summary report. If you look at the summary report, it includes a wide range of reliability indices such as availability of the system, average system interruption duration, and average system interruption frequency, as well as some other well-known reliability indices here. So in practice, once a switching action happens, it's not necessarily the case that 100% of the load can be transferred, mainly because of the operational constraints that are tied with the load flow results after the power restoration. Let's see an example here. So I go to the unbalanced load flow study and run the load flow study for this system. Let's zoom in a bit here, and we can see that the amount of power that is supplied by this utility is about 41 megawatts. So if I'm using this DG as the backup generator for my system, then I should know that if the capacity of the DG is not as large as this value, then anything beyond that will be cut off in practice. As another example, let's look at the current that passes through this cable. We can see that it's 312 amps. So if we wish to transfer the load in case of a failure on that cable, the cables that are within this alternative path all should have the capacity to carry this additional amount of current. Another constraint is related to the voltage of the buses. As you may know, the operational constraint of the system includes the minimum voltage of the buses. So in case a failure happens on this bus and the load is transferred through this switch, let's look at the load flow results here first. As we can see, after the load is transferred to the upstream, if we look at the voltage of the buses, we can see that it goes as low as 91%. So if we are having some special considerations on the minimum voltage of the buses, it means that we cannot necessarily transfer 100% of the load from downstream to the upstream after a failure on this bus. So in ETAP 24, to have a more realistic reliability assessment study, we have added this load flow constraint as an option to the reliability assessment study. So to run the reliability assessment study with the load flow option, first we go to the reliability assessment and open the study case editor. As we can see, we have the load flow checkbox here. So once you check this checkbox here, the additional edit boxes related with the load flow options are shown here. If you are already familiar with the unbalanced load flow study using ETAP, you may have noticed that some of these edit boxes are shared with the unbalanced load flow. For example, the generation category of the supplies, the initial guess for the load flow calculation, as well as the maximum iteration and precision of the study. In addition to that, the minimum load point voltage, which will be used for the calculation of load flow constraint, can be added here, which is in this case 98%. So once we run the reliability assessment study using the load flow option, ETAP calculates the load transfer rate based on the load flow constraint of the system, and this time the reliability indices will be calculated in forms of expected values with respect to the load transfer rate, the switching time, and MTTR of the system. Let's have a quick example here. So I run the reliability assessment this time with load flow option. And then from the report manager, I go to results and create a load transfer rate report. So this is the report for the load transfer rate. Here we can see that we have the fail element. Indeed, it lists all of the elements that are subject to failure. Then it calculates the amount of load that needs to be transferred upon failure of each of these elements. And it identifies the most critical element based on the load flow constraint associated with the failure of each of these elements. For each critical element, we report two transfer rate. One is corresponding with the power constraint, the other one is corresponding with the voltage constraint. And then the minimum of these two will be used in the calculation of reliability indices for the system. So if we look at the critical element for the failure and the utility, we can see that it is the generator 1, which is our backup generator. And because of its capacity, the maximum transfer rate here for the power will be about 86%. So it means that 86% of the load can be transferred through a switching action, while the remaining 14% needs to be interrupted and restored after the repair is completed. So to have a quick review, I'm gonna just change the capacity of this generator to a smaller value. So I go to the rating page and change the 30 megawatt to like 20 megawatt and rerun the reliability assessment and create the same report. So we go to the same elements here, and we can see that because we further decreased the capacity of the backup supply, the load transfer rate has been decreased to a smaller value. As the final example, to have a quick review between the reliability assessment using load flow and without load flow. So I have defined two scenarios here. First, I run the reliability assessment without load flow and create a summary report for that. And then I run the reliability assessment this time with load flow and create the same report for that. So let's put these reports side by side to have a quick comparison between the reports. So let's compare the reliability indices that are reported for the system with without load flow and with load flow. As we can see, for the availability of the system without load flow is higher than the availability of the system with load flow. Also, regarding the interruption duration, the interruption duration calculated without load flow is smaller than that of the case with load flow. Also, the electrical energy that is not supplied is much smaller than that of the case with load flow. So in general, it shows us that once we run the reliability assessment with load flow study, it gives us more realistic results because, as we discussed, it's not necessarily the case that we can always transfer 100% of the load because of the load flow constraint, unless the case that the capacity of all of the elements in our system are designed such high that the 100% transfer is available to us. In addition to that, once we run the reliability assessment with load flow and we'll look at the load transfer rate, it generally gives us a good insight about the bottlenecks of the system, such as those elements that are preventing the reliability indices to be higher because of the load flow constraints, such as the capacity of this cable or the capacity of the other cable. So in general, it gives a valuable insight about the constraint of the system while we are running the reliability assessment study as well. With that, I would like to thank you for watching this video. We highly encourage you to switch to ETAP 24 to see all the new stuff that we have added there, including the reliability and study enhancement. And please feel free to share your feedback with us about all of these enhancements. We are looking forward to hearing back from you.